Hello, welcome. So in this video, first we define totally disconnected spaces, and then we proceed to show some results on connectedness. State and prove. We will prove some results on connectedness. Okay, a space is a topological space is called totally disconnected if each of its components are single points. For example, let's consider this space X that contains 4 points 1, 2, 3 and 4, and each point is separated from the other point. So they are here the components are there are 4 components. 1 is a component, 2 is another component, 3 is another component, 4 is a component. So each of these components contains only 1 point. Then next example is X is the set of counting numbers. We consider the set of all counting numbers, and that set then contains other elements 1, 2, 3, 4, 5, 6, etc. Okay, all these points are also separated points, and they act as components. And then the third example is the set of all integers. See, set of integers contains set of all integers contains negative integers, 0 and positive integers. So that's also a completely disconnected space. And fourth example is the set of rational numbers. It's also this set is also this space is also a completely disconnected space, because we know that between any two rational number there exists an irrational number. See, you take two rational numbers A and B, and between A and B you can find a irrational number. Okay, and that property of existence of irrationals between any two rational numbers makes it clear that any two rational number stands as a single unit, and that can act as a that can make a component in the space of all rational numbers. We now discuss a result, the theorem 5.21. We prove that homomorphism H from X to Y between spaces X and Y induces a one-to-one correspondence between components of X and components of Y. See, we have a homomorphism. H is a homomorphism which is defined from X to Y. So X and Y are two topological spaces. Clearly, X can contain components and Y can also contain components. Okay, components are the connected subset, maximal connected subsets of a topological space. And then this existence of the homomorphism can make one more thing sure, that if there exists a component in X, C is a component of X, then you know that image of C can exist in Y, that is H of C. So if C is a component of X, then what is the image of C under the action of the homomorphism? It is H of C. Then H of C will be a subset of Y, and that H of C will also be connected. You know, we have proved that. Yeah, earlier we have proved that the connected parts, image of connected parts are again connected when action of a continuous function is applied on a connected part of a topological space. See, and using that, you know, we can say that HC is also connected, and thus what we are going to get is that suppose there are 10 components, and then their images are present in Y, and their number will also be 10. So if there are only 5 components in the space X, then corresponding images will be in number 5. The number of such images will be 5. And thus we have a one-to-one and one-to correspondence between the components of the first space to the components of the second space. So that is the meaning of this result, and we want to prove this. So we shall show that if C is a component of X and F from X to Y is a homomorphism, and then FC is a component of Y. See, first thing we want to show that see f of C, that is the image of C under the action of the homomorphism F will be a component of Y. See, F is 1 to 1 and on to. We know that, these are the facts about the homeomorphism. F is 1 to 1 and on to. F is continuous. F inverse is also continuous. Okay, and then since connectedness is a topological property, okay, you can just recall that connectedness is a topological property. In some previous video we have proved that, we have stated and proved that connectedness is a topological property. Okay, for as a help, you can I can suggest that theorem number 5.4 or something. Yeah, it's 5.4 something. Okay, that is not completely given there. Okay, just a minute. Okay, 5.4. It is the theorem number is 5.4. You can refer that theorem. Then the image of C. The image of C with respect to F is connected. Okay, therefore using that theorem, applying the theorem, we can see that the image of C with respect to with respect to the action of the homeomorphism F is connected, that is FC is connected. Next we shall show that FC is not contained in any other bigger connected set in the second space. So what we want to show next, we want to show that F of C is not contained in any other bigger connected subset of the second space. Yeah, suppose that F of C is contained in A. What do we think? Yeah, we suppose that F of C is contained in A, and A is a connected subset of Y, where A is a connected subset of Y. Okay, since F inverse is defined from Y to X. Okay, F inverse is the function defined from Y to X. It's also a homeomorphism. So when F is a homeomorphism, F inverse is also a homeomorphism. F inverse, which is defined from Y to X, is also a homeomorphism. Then F inverse of A is connected in X, and also that can contain C. F inverse of A is connected in X, and that contains C. But okay, that can contain C as a proper subset. But you know, C is the biggest connected subset of X. That's why we call it a component. So since C is a component, C must be that F inverse of C cannot be, and since C has the maximum size, so C cannot be contained in any connected subset. Therefore we get it easily that C is equal to F inverse of A. Thus we get that C must be equal to F inverse of A. Thus it is a contradiction to the fact that since C is a subset of F inverse of A, it's a contradiction to the fact that C is a component of X, and therefore FA is a component of Y. So we must correct it, that since we get the contradiction here, we have to correct that F of A is a component of Y. Thus F includes thus F induces a one-to-one correspondence between the components of X. Thus F induces a one-to-one correspondence between the components of X and the components of Y. Okay, and that's the end of the proof. Next, see, we want to discuss connected subsets of the real line. We want to discuss some properties of connected subsets of the real line. You know about the real line. What are the connected subsets of the what is the nature of connected subsets of the real line? So after discussing some one or two results that are included here, the nature of the connected subsets of real line will be clear to you. See the lemma. For that we require a lemma 5.22. A non-empty subset A of R is an interval if and only if for each pair C and D of members of A, every real number between C and D is in A. See, we choose a non-empty subset. Let A be a non-empty subset. A be a non-empty subset of R. we can show that it's an interval. This non-empty subset is an interval if and only for each pair C and D of members of A or elements of A, every real number between C and D is in A. Now, in order to prove this, if A is an interval, and then the stated property is follows from the definition of the interval. Okay, so first of all we can think that A is an interval. If A is an interval, then the stated property follows from the definition of the interval. Now to prove that, to prove the conveys, so we have to prove this result in both direction. So if A is an interval, then we know that that property is very clearly possessed by that interval. Now to prove the conveys of that property, conveys of the statement, for that we consider a subset A of R having this property, having the stated property. Depending upon the cases whether or not A has a least upper bound or greatest lower bound, and whether or not these bounds, if they are existing, belong to A or not, then we can break the proof into different cases. See, I repeat, depending upon the cases whether or not A has a least upper bound or a greatest lower bound, and whether or not these bounds, if they are actually existing, only then we want to think about whether these bounds are present in the set A or not. They are existing, they actually belong to A, and we can break the entire situation, entire case into different sub cases. So case 1. In case 1 we have neither a least upper bound and nor a greatest lower bound. That is, A has, in this situation we consider that A has neither a least upper bound nor a greatest lower bound. Then for every x belonging to R, there exists two elements C and D in A, such that C is less than x and D is greater than x. So x is an element of A, and hence A equal to the entire real line, and that's R equal to minus infinity plus infinity. The entire real line minus that extends from minus infinity to plus infinity. And now case 2. A has a greatest lower bound. A has a greatest lower bound. That's A, and which does not actually belong to A, and has no least upper bound. Then the real number x less than or equal to A does not belong to A. Then this real number, then the real number x having the property that x less than or equal to A, then these kind of real numbers x less than or equal to A does not belong to A. So if y is greater than A, then y is not an upper bound of A. So, and there exists D greater than y. Such that D is an element of A. Similarly, y is not the greatest lower bound of A. So there exists C which is less than y. There exists C less than y, and that C is an element of A. Since C is now combining all these, we get that C less than y and less than D, and also C and D are in A, and therefore y is an element of A. Thus A is nothing but the open interval A infinity. Thus A is equal to A infinity, and A is an interval. Next case, as an example of the explanation, we consider the next case, the third case. In this case, A has a least upper bound, and it has it is not present in A. It has a least upper bound, but it is not present in A, and it has no greatest lower bound. Let B be the least upper bound of A, and then A contains no real number x which is greater than B. See, in that situation, A cannot contain the real numbers having the property that the real number x is greater than or equal to B. Let y be less than B. Let's take the real number y less than B. since y is not a lower bound of a, and there exists c less than y, c that is less than y, and c is an element of a. Since y is not the least upper bound of a, so there exists d in a such that y is less than d, and therefore c is less than y less than d, and c and d are elements of a, and therefore y is an element of a, and hence we get that a is equal to the open interval b plus infinity. So then also it's an interval. Thus in all the situation, in all the cases that we have seen, we finally got that a is an interval. So by extending these steps of the proof in this in a similar fashion, then we can show that in all the remaining cases also we are going to get that a is an interval. Thus we can conclude that proof. Okay, next we are coming to the real theorem, that the original theorem, which states that connected subsets of R are precisely intervals. So this theorem states that connected subsets of a real line are precisely the intervals, and we know that every interval is connected. And so it remains to show that if B is a subset of R and not an interval, then it will be disconnected. So what actually we want to show? Since every interval is connected, we know that every interval is connected. So it remains to show that if B is a subset of R and it is not an interval, if it is not an interval, then it will be then it is disconnected. Okay, if B is not an interval, suppose B is not an interval, and using the lemma 5.22, we can find a number C. There exists, we can find, or we can choose a number C and D in B such that C less than Y less than D, C less than Y less than D, and Y is not an element of B. Yes, because B is not an interval. And then you can choose, then you can define u equal to minus infinity up to y, the open interval, and v equal to from y up to plus y up to plus infinity, the second open interval. Two open intervals thus we can define, and these are two open intervals, and the following are true for this open interval for u and v. C is a subset of u intersection, C is a subset of u intersection B, and so u intersection B, sorry, C is an element of u intersection B, C is an element of, C is a number, C is an element of u intersection B, so you see u intersection B is non-empty. D is an element of v intersection B, so v intersection B is non-empty, and B is a subset of u union V. Also u intersection B intersection V intersection B is empty, so u intersection B intersection V intersection B is empty, and that means this set u intersection B and V intersection B, u intersection B and V intersection B can make a disconnection for the space B, the subspace B, and hence B is not connected, so B is disconnected. So every connected subset of the real line must be an interval, and hence we can conclude the proof. Okay, thank you.